So this is my brief video on a first semester, first year pure mathematics project. It's relatively simple, but I spent long enough writing it out in LaTeX that I thought it was worthwhile enough to make a video on it. It's about the completeness axiom, Infima, Suprema, and bounds of a set. So basically, kind of foundational set theory stuff. Not proper set theory, but I think it's interesting enough, especially when you get to additivity and multiplicity of Suprema, which I think is quite intuitive, but maybe isn't thought about as easily. Um, so this, I have my PDF on the left, and I have, let's change to a pen. I've redacted my name and stuff throughout, but that's it. So I'm going to write on the right hand side, and meanwhile the PDF will be there. So basically, what is we'll just write in pink. What is a set? It's just a collection of numbers. And it doesn't repeat. I put an example in here, which, well, it's a very, very simplistic example. But before we get to that, I think we should talk about the types of numbers that we encounter, like the number systems. We have the natural numbers, we have the integers, we have the rational numbers, and then we have the real numbers. And we're not going to deal with complex numbers because this is real analysis, right? This is basic real analysis. No complex analysis, right? I mean, we don't need to go into, but we know I is the square root of -1, right? And these are all subsets of each other, so the natural numbers are a subset of the integers, are a subset of the rationals, are a subset of the reals. A natural number is just positive whole numbers greater than or equal to 1, so 1, 2, 3, dot dot dot, plus infinity. Integers are just any whole numbers, including 0, minus infinity, dot dot dot, -1, 0, 1, dot dot dot, plus infinity. A rational number is m divided by n such that m and n are themselves integers and n is not equal to 0 because otherwise undefined if you divide by 0, obviously. So this is just our basic number systems. Let me write that down. Our basic number systems, right? I go over this. Let's see where we are. Here. I can do that nicer. Let's choose our highlighter. Yeah, here we go. We can probably do that nicer still. Just do that. There, well, good enough. Right, so they're all subsets of each other, and that's kind of the foundation of what we're going to use. So let's turn back to our pen. Right, so we have this basic example here. I think this is a kind of a good way to start. We do work on what we call the real line, so it will be to plus infinity, minus infinity, which is effectively all numbers, right? Because a rational number is anything, almost all normal numbers, right? So 0.01 is just 1 divided by 100, right? And then other things that are irrational, we might write as like rational complement, or stuff like pi, e, etc. So they would kind of be outside that, but still within the rails. So it just goes on forever. It's an infinite number line. And but let's say that we use instead the subset of integers or natural numbers. It doesn't really matter. We have this set A equals, and then set notation 1, 2, 3. This is all that's within the set, 1, 2, 3. And when we start talking about sets, we need to talk about bounded sets, right? And this means for a set to be classified as bounded, it needs to be two things: bounded above and BDD, bounded below. It needs to be both, right? This is important. Basically, we define something as bound. No, let's talk about it this way. Let's have well, we'll call this, the set is A, right? And all the elements are A, lowercase a. These are the elements. Elements of the set. Right, say we don't know what they are. Let's call X is an upper bound if for all A belonging to A, so for all elements A belonging to the set A, there exists X such that X is greater than or equal to all elements A, and an element Y, not element, number, we should be specific, is a lower bound if for all elements belonging to the set A there exists a number Y such that Y is less than or equal to A. And you might think this is obvious. It could be 1 would be the lower bound, 3 would be the upper bound, which is correct, but this criteria is very wide, right? 4 is also an upper bound because 4 is greater than or equal to 1, 2, and 3. So would 5, so would 999. And likewise on the opposite side, 0, minus 20. It doesn't really matter, but we can see the utility in being specific here. Let's highlight this. That might not come out too clearly. Let's choose a nice color. Right, we're trying to speak more specifically about these ones. And what do we call these? This is what we call the greatest lower bound, and this is the lowest upper bound. And we have special names for these. The greatest lower bound is called the infimum, or the infima. Well, infima is a plural, and suprema or supremum or supremum, sorry, is a singular. It would be suprema for a plural, right? This is our special thing that we're trying to focus on. Before we get to that in more detail, we should briefly go over the idea of intervals. I've written about it here. Oh, that's not neat. We'll just use a highlighter. Basically, we're going to get to this in an example, but when we talk about sets, this A, B, and we can do A, B, and what will be another good one? A, infinity. Right, this is a closed bound, and this is a closed bound, which means that we have some kind of number system, and A is one bound, and it's included within the set, and B is another bound, it's included within the set, and all the numbers are in between, including A and B. But here, for this example, A is not within the set. It's everything, when you get really, really close, they're going to start to converge. And B will be in the set. Because you might think, oh, it's real analysis, everything is going to be like a solid line. And it's like, well, it might be a solid line, but it might start to converge. And that could be like, it gets really, no, it would be the opposite. It would be really spaced apart, and then it starts to really closely converge to whatever this bound is as Because when we do this, we're going to have to take limits. And because usually when these questions are posed, they give us a kind of sequence or series. Say sequence notation xn, and we're going to have to find the limit of xn as n goes to plus minus infinity, because when a real line, it goes to plus infinity, it goes to minus infinity, and we're trying to find the limits as we can have some sequence, 3n over 2n, right? If you make this minus 10, or 10 and 10, you're going to get different values. And these are going to be really extreme values, like bound in your set. They're going to be the highest values you can possibly get. They're going to be like a maximum and a minimum. And you might think maximum and minimum would be the right terms, but we're going to get more specific about that soon. And obviously infinity is unbound, because then we get into things such as we have finite sets, infinite sets, and countably infinite sets. Yeah. So when we talk about the idea of a supremum, we'll just highlight this again. So I think it's very important. I'm not sure how effective that is of a highlight, but there we go. When we start talking about supremums, we're basically saying, imagine we have a number system, a real number system, and we go from plus infinity to minus infinity, and say this value, let's say it's a closed set. It doesn't matter what it is. 3. So let's say 3 is included within the set, 9 is included within the set. They're both elements, and then there's a bunch of elements. As you can see, I've done the same here. I denote them with vertical. Oops. I denote them with vertical lines. There's several elements within the set. Right, it doesn't matter what it is. This is a set A, or it's a sequence xn. It doesn't really matter. But the idea is, our supremum, we've established that this is an upper bound, this is a lower bound, but there's also, countably, whatever, infinite, many upper bounds. But we're saying this is the lowest upper bound. But how are we sure of that? It's kind of, we prove this with a proof by contradiction, because we're saying 9 is Suprema, is the Suprema, alright, will be correct, is the Suprema S if and only if, that's what IFF means, if the following criteria holds, that for all A belonging to the set A, there exists an A such that S minus epsilon would be less than A. What does this mean? Let's change colors. Do we have a nice one? Why don't we do gold? Basically, that means that if we take away a little tiny finite distance, minus epsilon, because when we do this, we usually like to clarify epsilon is an arbitrarily small difference. Right? It's a tiny difference, microscopically small. It's not 1, it's not 0.1, it's not 0.01. It's so small it doesn't really matter how small it is. But when we talk about these number systems, we can act like they're discrete values, but in all reality, they're going to be so many. It's a continuum, right? This is why we talk about the completeness axiom. We'll get to that, by the way, because it's a completeness. It's a continuum of values. So if we take away even a tiny little thing, there'll be some value, say here, such that for all the elements in set A, there exists an A, our golden one, such that S, which is 9, minus epsilon will be less than A. So this means that if we take away even a little bit, there will be something else which is bigger than this difference. Therefore, 9 must be the supremum. Otherwise, there's a contradiction, and we can, indicate proof by contradiction like this. Some lectures like this, but I think this is strange. And it's a similar proof for, let's go for copper. I'm not sure ocean. I'm not sure what ocean means. Let's see, where are we now? It's the same principle that, scroll down a tad. Where am I now? Here. Free is the infima if and only if for all A belonging to the set A, there exists an A such that, well, we'll call it I for infima. It's just the way we're notating it. I plus epsilon will be greater than some A, and we always write epsilon arbitrarily small. So then once we visualize this above, plus epsilon, hey ho, say there's one, there could be several values of which it's greater, of which it goes beyond. So we're basically saying this is the infimum free, because if we add even a little bit, there's some value which is now, it's now greater than, because it's going to jump ahead, if you see that arrow there. So this is our these are our core concepts. But then we also start talking about maxima and minima. We say the max is the supremum if the suprema lies within the set, and the minimum is the infima if the infima lies within the set. Let's change back to a more normal color, because sometimes we have number systems where the values will converge really, really close, right? Remember I was saying about how maybe values are more spaced out and then they become really, really converged, but they're never going to actually reach this value. And we're going to get to this in a moment. This is when it gets a bit more interesting. But before we do this, well, we can always touch on the completeness axiom. I don't think this is overwhelmingly important, but it is it's what we've already discussed effectively. Every non-empty set of real numbers which is bounded above has the smallest upper bound, which is a supremum, and every non-empty set of real numbers bounded below has the lowest upper bound, an infimum, which kind of makes sense, just logically. Because if we have a set, it's non-empty, as in there are elements within it, because an empty set would be, this. This just means an empty set, which is useless, really. I mean, you might start talking about this in linear algebra and so on, but it's not overly useful at the moment. If it's bounded below, well, there has to be a suprema, but the suprema doesn't actually have to lie within the set, which is kind of the interesting idea. You might think, if I have a bunch of values, right, surely the kind of limit point that they're all leading to would be within the set, but not necessarily. And we're going to get to that in an example. Just make that a bit neater. Yeah, just make that a wee bit neater. Plus infinity minus infinity. So this is the example I used. There's a tiny little mistake here. I noticed this recently. It's supposed to say s equals 3 to n minus 1 over 2 multiplied by 3 to n. I wrote 2 to the minus. I only noticed that now, but it's important to notice. So this is our set of values, right? It's a sequence. But for simplicity, just call it x to the n, because it is a sequence that depends on n. So this is quite good because for natural number sequences, you know very well that you have a fine cutoff point, because what is the smallest natural number is 1, right? So let's say what's 3 to the 1 minus 1 over 2 multiplied by 3 to the 1. We're going to get 2 over 6 is 1/3. So this is going to be our smallest value. So 1/3, and we know this actually does belong within the set because for n equals 1, it is within the set. We could call this maybe, you know, like set notation. Well, that would be more neat, not this. But then what is the highest value? And, you know, I'm not going to go over limits in like an incredible amount of detail because that isn't this. Limits are important, but this isn't the focus. Further on in real analysis classes, they'll give you all these kind of axiomatic limits that sometimes they prove them, sometimes they're just kind of established as fact and you kind of go off that. But I mean, if you really want to cheat, you could just do this into your calculator, you know, set n to 99. Just make it as high as possible. Because for natural numbers it's especially easy because it goes from 1 to ... to infinity, plus infinity. You don't have to worry about the other side. Normally, you would do the limits both ways. So you would take the limit of xn as n goes to plus minus infinity, you know, as separate limits, almost. But for our sakes, we just know. I mean, you can prove it, but that's not the point right now. The limit of xn as n goes to plus infinity is going to be 1/2, right? 1/2. But we're never going to reach it. You could do n equals, well, your calculator's going to run out of memory. You could do n equals 20, n equals 30, n equals... You can plug this into your calculator. Obviously, I would recommend use the, you know, proper methods, but that's not the point here. And you're going to get really close to half. Maybe you get 0.49, 0.499. You're never going to reach a half. So this is all we need to know. But a half clearly does bound our set. We have established this. So we still call this our lowest upper bound, or our suprema. And this is our infima. But as the infima I belongs within the set A, we can therefore call this a minima as well. It's both. But this is, our suprema does not belong within the set A. So it is not maxima, which is important. We would use this with the same notation as we had before, that for all A belonging, I'll just do the one for the infima. There's not really a purpose in wasting time. For all A belonging to the set A, there exists an A such that I plus A will be greater than A. Therefore, I is an infima. And we obviously also don't forget to even mention that we can say I, because of being a bound is a pre-requirement for this to even make any sense at all. I is a lower bound as for all elements belonging to A, I will be less than or equal to A. So that's a prereq, that's important to even mention. But when we take the limits, we should be clear of the actual terms. Let's change this back to gold for fun. When we take the limit of xn as n goes to plus infinity, we can call this the limit superior And when it's n to minus infinity, we call this the limit inferior. Superior, inferior, limit, dot dot dot, dot dot dot, dot dot dot. It's just a good thing to notate. Is there anything else? Well, we can start to talk more about what I think is an interesting thing, which is additivity and multiplicity. I'm just going to show the proof for Suprema, but it's very similar with Infima. It's the same line of logic, and I have diagrams here in the PDF to kind of prove it as we go along. So, where are we now? Our pen. Proof of additivity of Suprema. So, let's say we have a real number line and we have two sets. We can just do them with closed bracket notation, it doesn't really matter. And we have set A and set B, and we should be, I'm just going to rub this out just to give us a little bit more room because there's going to be a large proof here. I'm going to change this to silver. I'll just write additivity proof dot dot, and we'll make our preliminary. These could be overlapping, which is very important to know. I'm just doing this here to make them seem more discrete, to make it more clear for us. But we're basically saying, here is our, let's change this to blue, our statement. If A and B belong to R, and they're both non-empty as well, they're both not the empty set, and they're both bounded above at least, then okay, so we're saying that we have a set called S. The set S is the addition of elements from A belonging to A and B belonging to B in no particular order, right? Yeah, S equals A plus B. So this could be any element in A plus any element in B. This is be very, very clear about this. All possible combinations, right? But we're saying these are bounded above, and by completeness, and by the completeness axiom that we have here, right? We know that they must have a suprema. So we can call the suprema of the set A alpha, and we can call the suprema of the set B beta, right? And this is an addition of two elements. The set S is one element from A and one element from B, right? But what does that mean? What is the greatest element in S? Logically, if this is any from A and any from B, the greatest element would be, I mean, it could be the greatest from A and the smallest from B, it could be two middling values, but the greatest element in S is going to be the greatest element of A plus the greatest element of B. But as we've defined that these are bounded sets, and by the completeness axiom, these are the greatest elements of A and B, alpha and beta. So the suprema of set S is going to be alpha plus beta, logically. And we can go into this in more detail by splitting the epsilons in half. But it is the same epsilon style Suprema. Well, and this also Infima. We can extend to this very easily. Proof. And that's kind of the core concept. As long as you understand that, it's actually not very difficult. And when we start doing, I think, multiplicity, we can go over that briefly and then we'll just finish up. So, proof of, let's write that properly, multiplicity. Same idea. This is just a graphic representation. It's not really meant to be taken overly seriously. Let's say we have a set A, we have a set B. They could overlap, right? It could be like this. We'll just undo that. But this just makes sense visually. And then we have a set. Well, we can make it larger to make it seem like it's multiplication. P. And the set, A, B belong to reals, and they're not empty. P is A multiplied by B. Right, this is our set P. Any value from A multiplied by any value from B. Right, so A belonging to A, B belonging to B. But it's the same line of logic as the greatest value of a bounded set is the supremum, the greatest value of a bounded set is supremum, therefore the greatest product of any values would be the product of the two greatest values, so it will be alpha beta would be the suprema of P, and it's a very similar proof that way. So it's not really that difficult to understand, but it is quite interesting. And it took me a very, very long time to make these diagrams in LaTeX. But I'll be honest with you, I did use, where is it? Scroll down. This isn't cheating, by the way. We were told we were allowed to use AI to help make the diagrams because it's very complicated. But even if you use the AI, it's not particularly helpful. I probably spent more time adjusting it, and then I kind of rewrote it myself. But I would recommend this textbook, Mathematical Analysis by K. Binmore. Oops. It is my primary recommendation, and is a source that I used for a lot of the quotations in this report, because it goes into kind of a lot of detail, but not really. Anyways, there we go.